So dear students, I was talking about graphical representations, about graphical expressions. Graphical expressions or graphical representations are extremely analytical and informative. Actually, there are two types of variables, dependent variable and an independent variable. Dependent variable changes its value corresponding to independent variable. How a particular dependent variable depends on independent variable, that relation, that dependence, that correspondence can be exhibited either algebraically or graphically. Such as previously we have done certain questions like S equal to GT square. Here S dependent on time and the dependence is being expressed, being exhibited algebraically. Now we can draw a graph also, S versus T graph also corresponding to that particular relation. So I mean to say that dependent variable depends on independent variable, and this particular dependence, this particular interrelation can be shown, can be exhibited, can be displayed graphically, and that approach also is very decent. There's also a very excellent analytical approach to display informations regarding this dependent and independent variable. So here in this particular slide, the same thing has been mentioned. Dependence of a dependent variable upon an independent variable can be exhibited graphically also. However, graphs involving a vectors, I mean there could be position time graph, there could be displacement time graph, there could be velocity time graph, there could be acceleration time graph, there could be acceleration versus position graph. Whenever a graph involves a vector, if it is a speed time graph, if it is distance time graph, no problem, no constant, nothing to bother about. But whenever graph involves a vector quantity, that can be done only for one directional case, that can be done only for one directional motion. Because in graphical representation, you can, a certain quantity, even though it is a vector, you can show it either to be positive or it might be negative. So graphs involving a vector quantity can be strictly drawn only for one directional case, and this is going to be a very, very important milestone point. Further also, you will further go into another later chapters of mechanics or further chapters of physics. Always remember that whenever graph involves a vector quantity, that is strictly for one directional case, dear students. So this point is very, very important, simple but very important point, very compact but very useful and important concept. So in one directional motion or rectilinear motion, there is immense, unlimited, sky is the limit, that kind of a scope of graphical numericals. In whenever you will go through a particular exercise book concerned to rectilinear motion, a big fraction of numericals, a big chunk of numericals will be from graphical side, will be graphical questions, and sometimes the student feel a lot of difficulty in dealing with them. But if you understand proper technique, proper concept to deal with them, there won't be any difficulty further. Following types of graphs can be given, can be drawn so far as one directional motion is concerned. In one directional motion, kinematical quantities are position, displacement, velocity, acceleration, etc. In one directional case, we can have following graphs: xt graph, vt graph, x versus time, position versus time graph, how position varies with time, or vt graph, how velocity changes with time, how velocity varies with time, or vx graph, how velocity changes with position, or ax graph, acceleration versus position graph. Lot of more scopes are possible, but prominently these are the graphs which could be drawn so far as one directional motion is concerned. Now here we have for a one directional motion, for one directional case, we have x versus time graph, position versus time graph, and we shall analyze this particular situation. We shall analyze this particular situation. We have x versus time graph for one directional motion. Particle moving along a straight line, its position varies with time. When time was 0, position also was 0, right here you see. And when time increases at a certain time, there is a particular value of position. This is a straight line. This graph is a straight line. Here x is directly proportional to t. In fact, x will be equal to constant into t. X will be equal to a constant c into t. C is a constant. Since xt graph is given, we can directly talk about velocity of the particle. Particle started from origin at t equal to 0, is moving along positive x direction. X increases with time. At lower time, x is lower. At higher time, x is higher. Particle is moving along positive x direction. These are the inferences, these are the conclusions after seeing this graph. We can directly talk about velocity of the particle right here. V is equal to, velocity of particle is equal to, velocity of particle in this case is equal to, V is equal to derivative of x with respect to time, derivative of c into t with respect to time, it's equal to c, derivative of t with respect to t, ultimately it is equal to c. So this is velocity of particle, and we can say that right here velocity of particle is constant. Particle moves along positive x direction with a constant velocity. Here velocity of particle is constant. Velocity of particle is constant. Velocity of particle is constant in this particular example. Particle moves with a constant velocity. Let us have another situation. Here again, for one directional case only, basically it is for one directional case. It is for one directional case. For one directional case, again we have x versus time graph, and graph this time is curved. At least in very firm manner, we can understand how to find velocity of particle when xt graph is given. You know, velocity is equal to dv upon dt. Here we have available space, and I'll write this particular point, or we can write here also v equal to dx upon dt. Derivative of x with respect to time. It means at any point, suppose this is a particular moment, t0 or t1, and at this moment I have to find velocity, means I'll mark corresponding point on the graph corresponding to time t1. Whatever point is on graph, I'll mark that particular point. I'll draw a tangential line right here. I'll draw a tangential line here. Here I'll draw a tangential line at this particular point to this curve, and I'll see what is the slope of this tangential line. I mean, I have drawn a line parallel to time axis, and then I'll see this particular angle theta. Tan theta is equal to slope of tangential line. Slope of tangential line drawn at this particular point, and this tan theta is nothing but dx upon dt. This tan theta is instantaneous velocity of particle at time t1. Tan theta is equal to instantaneous velocity v instantaneous at time t1, instantaneous velocity of particle at time t1. So this is a general method of finding instantaneous velocity. In this situation, you see, if I consider a point before time, right here, before this time t1, here if I see a certain point. Here if I check a particular point and draw a tangential line, it is making larger angle theta 1 as compared to theta. This angle is bigger. Larger theta 1 with time axis, I mean slope tan theta 1 is bigger than tan theta at this particular moment. With time, I think the slope is decreasing. Tan theta decreasing with time. At lower moments, at earlier moments, tan theta is bigger. Theta remains less than 90. 0 to 90 range is being considered, and tan theta, I mean theta gradually decreases, so tan theta gradually decreases, and here we can say speed is, magnitude of velocity is decreasing. At each and every moment tan theta is positive. At each and every moment velocity is positive, but yeah, magnitude of velocity is continuously decreasing, and here we can say velocity and acceleration are oppositely directed. Dear students, very important point. In this example, we can ultimately conclude that velocity and acceleration are opposite to each other. Reason, magnitude of velocity continuously decreases with time. So here in this example, we can say, we can write certain conclusions. Here velocity is always positive. Whatever part of graph is given, as per that we can say velocity is always positive. Magnitude of velocity decreases with time. Speed of particle decreases with time, and so velocity and acceleration are opposite to each other. Opposite to each other. So here we can make these conclusions after seeing this graph, that this is the concerned graph. Here you see, this is the concerned graph, how this curve goes on. You have seen that, observe that. Velocity is always positive, tan theta I got to be positive always. Theta is acute angle less than 90, between 0 to 90. Magnitude of velocity decreasing with time, and velocity and acceleration are opposite to each other. Velocity and acceleration are opposite to each other. Reason, speed of particle decreases with time. I hope you understood it. We shall go upon one more similar kind of example. Here you see, again a similar style question, but the curve is now concave upwards. Curve is now concave upwards. It is again for one directional motion. This graph is again for one directional motion. This is again given for one directional case, one directional case again. X versus time graph is given. XT graph is given for one directional case. This is a curved graph. The relation between X and T is shown by this particular curve. You consider a time moment T1, and at time T1, this is the corresponding point on graph. Now you select another time T2. At time T2, we have another point corresponding to T2. We have this another point on the graph. Draw tangential lines at these points. Draw tangential lines at these points. So here the tangential line drawn. Here the tangential line drawn is like this. Here this is tangential line drawn, and this angle is theta 1. This angle is theta 2. Theta 1 and theta 2 less than 90 degree. Theta 2 are less than 90 degree. Tan theta 1, tan theta 2, both are positive. Both are positive. Tan theta 1, tan theta 2, both are positive. Tan theta 1 is equal to velocity at time t1. Tan theta 2 is equal to velocity at time t2. tan theta 1 is velocity at time t1, tan theta 2 is velocity at time t2, instantaneous velocities at t1 and t2. How to find? You know well, we have done that. Now theta 1 is smaller than theta 2. So tan theta 1 also is less than tan theta 2. It means velocity at t1 is less than velocity at t2. Both the velocities are positive. Particle is moving in positive x direction, but magnitude of velocity at t1 it is smaller than magnitude of velocity at t2, and this kind of trend will continue. So in this situation, particle moves along positive direction first of all.